Welcome to the deep dive. Okay, so today we're really going to dig into something absolutely foundational. I mean, the architecture that pretty much runs the modern web, restful web services. If you're involved with cloud infrastructure, maybe building microservices, or, just curious about how data manages to flow so efficiently everywhere, well, this deep dive is definitely for you. Our mission, really, is to equip you with a solid understanding so you can quickly get why REST, that's representational state transfer, why it totally changed the game for APIs, and, how its fundamental ideas, the ones from the original concepts and best practices, actually allow for massive, massive scale.
Yeah, it's crucial to think about the world Roy Fielding was seeing back then, late 90s, before 2000, getting servers to talk to each other, especially using the established protocols.
Yeah.
It was incredibly rigid. APIs were often tightly coupled, really complex, sometimes proprietary, then just a nightmare to maintain. They weren't built for the kind of easy global access the internet was promising.
Right. So when Fielding and his team introduced REST, it wasn't just about making things easier. The goal was uh, global standards, simplicity itself, really leveraging what was already there, HTTP. And that simplification. It cut down development time, sure, but it also drastically reduced the bandwidth needed.
Exactly. And that simplicity, that's the real aha moment here. Because REST is straightforward to cache, it's maintainable, and crucially, it doesn't demand complex state tracking on the server side. That just unleashed the true power of APIs.
Hmm.
Honestly, without REST, things like modern cloud computing or the huge shift to microservices, they probably wouldn't look the way they do today.
Which brings us right to the main question. What exactly makes a web service RESTful? Let's start breaking that down, maybe beginning with the core concept in the REST world.
Absolutely. The absolute center of REST is the resource. Forget objects or web pages for a moment. Just think of every single piece of content. Could be text, an image, dynamic data like, say, a user profile. Think of it as a resource. The REST server provides access to these resources, and the client is what consumes or modifies them. It fundamentally shifts the focus from verbs, like get user, to nouns, the user resource itself.
Okay, so if the resource is the noun, then the URI, the Uniform Resource Identifier, that's basically its unique address, right? It's a global name tag. That's how the client pinpoints it, using that familiar structure we see everywhere.
Yeah.
Protocol.service name, resource type, or resource ID.
Precisely. And maybe we should quickly clarify the difference between URL and URN, because they often get mixed up. A URL, the locator, tells you exactly where the resource is and how to get it. That's the typical web address. A URN, the name, identifies the resource uniquely and persistently, but doesn't necessarily say where it is. REST uses that URI structure to make sure everything's identified globally without ambiguity.
Okay, got it. Now let's talk about the real magic ingredient for REST scalability, statelessness. How can a server possibly handle, millions of clients efficiently if it doesn't even remember who they are from one moment to the next?
Right. This is so critical, and it's where simple definitions sometimes fall a bit short. Statelessness means the server holds zero client session information between requests. None. So every single request coming from the client has to carry all the information the server needs to process it. Think of it like this. You wouldn't walk into a coffee shop and just say the usual, right? You'd say, hi, I need a large latte with oat milk, and my name is Alex, every single time.
Ah,
Oh,
okay. So the client has to constantly provide that context, maybe a session token or authentication details in every request header.
exactly. And the brilliance of this, architecturally speaking, is huge. Since the server doesn't care about past requests, you eliminate session stickiness when load balancing. Any server in your big cluster can handle any request from any client, anytime, if one server goes down.
The load balancer just sends the next request to another one.
And because the client sends all the context, that new server picks it up without missing a beat. It doesn't need any prior knowledge.
Wow, okay. That makes scaling horizontally just massive. You can just throw more standard servers into the mix without worrying about replicating session data between them.
It simplifies the infrastructure deployment massively. But let's be fair, there's a trade-off. That responsibility for managing the state, for passing that session identifier along every time, that falls completely on the client.
That seems like a worthwhile architectural trade-off in many cases. Okay, shifting gears a bit. We know how to find the resource, the URI, and why the server doesn't need to remember us, statelessness. How does the client actually tell the server what to do with that resource?
That's the other elegant part, leveraging standard HTTP. The interaction is driven by the standard HTTP methods. These are basically verbs, and they map almost directly onto the basic actions we call CRUD: create, read, update, and delete.
Okay, let's quickly run through the main ones.
Sure. Key T is for reading or fetching resource details. That's your read. P piece is generally used for creating a brand new resource. The create. PT is for updating an existing resource, or sometimes replacing it entirely if it's already there. That's update. And delete is pretty self-explanatory. It removes the resource. Delete.
And you mentioned PAT-CH earlier for smaller changes.
Right. PAT-CH is for when you only want to modify a specific part of a resource, not the whole thing. But now we get into some really important technical details, things that really separate robust API design from something fragile. Idempotency and safety.
Yeah, I always find this useful because it clarifies why you choose one method over another, especially when things seem similar. Let's start with safety. What makes a method safe?
Okay. Safe methods are operations that absolutely guarantee they won't change the resource's state on the server. They're purely for retrieval. Think get, head, options. Because they're safe, clients or intermediaries can cache their responses without any worry of causing unintended changes.
Makes sense. And idempotency. That sounds more complex.
Idempotent methods mean that making the same request multiple times has the exact same effect as making it just once. After the first successful call, the system's state related to that resource doesn't change with subsequent identical calls. Get, put, delete, head, options. Those are typically idempotent.
Okay, wait. So POT and PAT-CH are generally not idempotent.
Correct.
The big confusion always seems to be POT versus POS. Both can feel like they're about updates or changes. Why is POST non-idempotent?
Okay, think about POST's typical use, creating a new resource within a collection. If you send POST users 10 times with, say, slightly different user data each time, or even if the server just assigns unique IDs, you'll likely end up creating 10 different user resources. The state of the user's collection changes with every call. That's non-idempotent.
Right. But if I use P2 to update a specific user, like POT users 456 with the same user details, and I send that 10 times, what happens then?
Well, the first call performs the update. The user resource with ID 456 now has that new data. The next 9 identical calls, they just overwrite the same resource, use 456 with the exact same data. The final state of user 456 is identical after the 10th call as it was after the first successful call. That's idempotency. The effect stabilizes.
Okay, that clarifies put for versus post, but delete. It feels inherently destructive, so how can it be idempotent?
It usually is because its goal is to ensure the resource is absent. The first delete user's 123 call removes the user. The server might return a 200 OK or maybe a 204 no content. If you then send delete users 123 again, the resource is already gone. The server will likely just return another 204 no content. The system state, user 123 is absent, hasn't changed between the first successful delete and the subsequent ones. The goal was achieved and stays achieved.
Ah, okay. That makes sense. The outcome is the same. Resource is gone. Right, let's pivot to that classic debate. REST versus SOAP. For a long time, these were the two main ways to build APIs. Why did REST end up becoming so dominant?
It really boils down to their core philosophy and architecture. REST is fundamentally an architectural style or pattern. It's flexible, lightweight, and leverages existing web standards like HTTP. SOP, on the other hand, Simple Object Access Protocol, is a strict protocol. It has rigid rules, mandates specific messaging formats, usually heavy XML envelopes defined by standards like WSDL.
Okay, so if I'm in a situation where I absolutely need things like guaranteed message deliver, maybe complex transaction management, or really strict security requirements, perhaps driven by regulations, that sounds more like a job for SOAP.
Exactly. SOAP, with its strict contracts via WSDL, provides strong guarantees around reliability, transactions, and security features built right into the protocol itself. It tends to be better suited when you're exposing complex business logic and need that tight coupling in those guarantees. But the trade-offs are significant. It's complex, generally only uses XML, and its operations are typically not easily cacheable.
Whereas REST offers a different set of advantages.
Yeah, REST generally wins on simplicity, speed, and flexibility. It's often better suited for exposing data rather than complex operations. It uses standard HTTP verbs, supports various data formats. JSON is king now, but XML, plain text, etc. are fine. And crucially, its GET requests are highly cacheable by browsers and intermediary proxies, which dramatically reduces server load. So you generally choose REST for simplicity, broad compatibility, especially with web browsers and JavaScript, performance, and scalability.
Makes sense. Given REST is pretty much the default now for modern APIs, let's touch on some best practices for actually implementing them, especially around designing those URIs, clearly.
Good idea. Number one rule, probably. Use plural nouns for your resource collection. So it should be products, not product, because you're dealing with a collection of products. Second, remember the client specifies the action using the HTTP method. get, post, etc. So absolutely no verbs in the URI name.
Gotcha. So instead of get user or create new product, it's get users and post products.
Exactly. Keep the URIs as nouns representing the resources.
Yeah.
And if you need to show relationships between resources, use nesting, but do it sparingly. Like author books clearly shows books belonging to a specific author. That's good. But try to keep that nesting shallow, maybe 2-3 levels max. Otherwise, the URIs become really long and hard to manage.
Good tips. Okay, we've established scalability comes from statelessness, but what about security? That's always critical. The source material mentioned REST doesn't really dictate its own security measures.
That's right. Because REST is an architectural style that works over protocols like HTTP, it basically inherits the security capabilities of that underlying protocol. Security isn't built in. It's a layer you must add. For secure communication, using TLS, Transport Layer Security, via HTTPS is non-negotiable. It's mandatory. HTTPS encrypts the entire conversation between the client and server, preventing eavesdropping, and it also authenticates the server to the client.
And even if a system uses something simple, like HTTP basic authentication, sending the username and password in the header, HTTPS is still essential?
Oh, absolutely vital. Basic auth, just base64 encodes the username.password. That is not encryption. It's easily reversed. If you send that over plain HTTP, anyone listening can grab it and decode it instantly. HTTPS encrypts the whole thing, including those headers. You just can't skip it.
Understood. Okay, for listeners who might be developers, let's briefly touch on how some major frameworks make building these REST services easier. In the Java world, there's JXRS.
Right. JXRS is the Java API for RESTful web services. It makes heavy use of annotations, things like @path, @getT, @post, @produces, @consumes. These annotations let you map your Java methods directly to specific URI paths and HTTP verbs, making the implementation quite declarative. Something often overlooked is its built-in support for handling asynchronous requests using things like java.util.concurrentFuture. That's really important for building responsive, non-blocking servers.
And what about the Spring framework? It's everywhere.
Spring, particularly Spring Boot, makes REST development incredibly simple, largely thanks to the @REST controller annotation. Traditionally in Spring MVC, you'd use @controller and often have to manually configure how your return values get converted into the response body, maybe using @response body.
Okay.
@REST controller is basically a convenience annotation that combines @controller and @response body.
Ah, so it automatically assumes that the methods in that controller will return data that needs to be serialized directly into the response body like JSON or XML, rather than rendering a view template.
Exactly. It handles that conversion, marshaling your Java objects into JSON, for instance, and unmarshaling incoming JSON into Java objects pretty seamlessly. It's a huge productivity booster and helps keep the focus on the business logic, not the plumbing.
Makes sense. And once you've built your service, how do you make sure it actually works correctly and scales? Testing.
Yeah, testing is crucial. For functional testing, does this endpoint do what I expect? Tools like Postman or Insomnia are indispensable. They let you craft very specific HTTP requests, set headers, send body data, and then inspect the response status code, headers, and body in detail. For documentation, which is also a form of testing in a way, Swagger, now known as the Open API specification, is the standard. It lets you define your API structure in a machine-readable format, which can then be used to automatically generate interactive documentation, client SDKs, and even run automated tests.
And for performance.
For checking how your service handles load and stress, you need dedicated performance testing tools. Apache JMeter is a popular open-source option, but there are many others like K6 or Gatling.
Right. We've covered a lot of ground here, from REST's origins as this architectural idea to how it gets implemented with modern tools. The impact is undeniable. REST really won out because it prioritized simplicity, leaned on existing web standards like HTTP, and used statelessness to unlock incredible scalability and flexibility.
Absolutely. And that focus on resources, on statelessness, while brilliant, also means developers are constantly making interesting design choices. The real art often lies in figuring out exactly what constitutes a distinct resource in your system and navigating the implications of keeping things truly stateless.
We did touch on the fact that statelessness, using HTTP, means setting up a new TCP connection for pretty much every request, which adds a bit of latency overhead. It's a deliberate trade-off for that architectural simplicity, but the demand for real-time instant interaction keeps growing.
And that leads to a really interesting kind of provocative thought for the future, right? We mentioned technologies like WebSockets. They're different bidirectional, faster for ongoing communication because they keep a single TCP connection open. reducing that setup overhead compared to REST's many connections. So given this increasing need for real-time data, developers have to constantly weigh things up. Is the stateless simplicity and broad compatibility of REST worth its inherent connection overhead for this particular use case? Or does the stateful efficiency of something like WebSockets make more sense, even if it introduces different complexities? Answering that question, when is REST's overhead acceptable versus when do you need something more persistent like WebSockets? That's becoming a key architectural decision that really dictates whether a system scales well or becomes a headache down the line.